Here's an example of what I was talking about in the vector line intro video. When we've got a point and a vector and we want the line through that point in the direction of the vector. So here the point is minus 6 comma 2. The vector is 3 1. And what we'd like is an explicit description of the line. Well, there's a few slightly different ways to write that description, but they all come from the same idea that we want a variable vector, or in other words, a vector function of, say, a variable t, and that's often thought of as time. You don't have to, but it's a very good way to think about it usually. And that's going to be r of t, I'm going to boldface that because it's a vector, equals, and what we figured out is that if I take this point P and promote it to be a vector, oops, and then I add any multiple, oops, I don't want those bold, normal, of the vector v, then I'm gonna have what I want. So first of all, let's just promote this point to be a vector. That doesn't require anything but changing notation. There's some subtleties there, but usually we almost ignore the difference between the two kind of guys. And so I can just write this out. This is going to be minus 6 comma 2, my base point, plus some multiple of 3 comma 1. Okay, I can do that vector addition. That's minus 6 plus 3t comma 2 plus t. And so if I want to get out of the vector terminology, then I can just say, okay, these are the x and y components of the vector, of this variable vector. And in other words, if I just change it back to round brackets, the points are of the form x comma y is just the same thing, but with round brackets. Just regular parentheses. Minus 6 plus 3t, 2 plus t. Or in other words, a very a somewhat lower tech way to describe it is just x equals minus 6 plus 3t and y equals 2 plus t. That's something you've seen before. That's a parametrized curve. It happens to be a straight line, but it's a special case of a parametrized curve in the plane, where we take a value t and we explicitly create an x and y, a point in the plane. And often we think of that as the motion of a particle, and that's how I'd like to think about this, as something starting here at time 0 and going off this way. Or let me say, not starting necessarily. When we started the stopwatch, we found it here and it was going this way. Maybe before we started the stopwatch, it was off here where the t values would be negative. Okay. There's one other way to describe this. So the symmetric equations, often we want to eliminate t, and we can do that by first solving for it. T equals x plus 6, move the 6 over and then divide by 3, but it's also equal to y minus 2, and there we go. Just ignore the t. Those are the symmetric equations for the line, and it's just a relationship between x and y. Now, of course, we're used to different kinds of y equals x forms for a line in a plane, but for 3 dimensions, it's actually pretty convenient. We're going to get equations involving x, y, and z. But I wanted to start with a simple example in 2 dimensions, partly because my picture looks so 2-dimensional. And I think that's all I want to do for this one.